Hi, in this short video, I want to go over calculation of a confidence interval for proportion. As an introduction to this, I want to describe what the mechanics are of sampling a population where the variable is dichotomous, like yes or no, diabetic or not diabetic, and so on and so forth. So let's think about this. Let's say I sample 1,000 people in a population. Oops. And I find that in that population that 200 people have diabetes and 800 people do not have diabetes. Okay, so what proportion of the population has diabetes? Okay, well, keep in mind, this is a sample that we've just taken. We've taken a sample of 1,000 people. That's a big sample. It's pretty reliable because it's so big, but we're dependent on the fact that it's random and there are no other confounders and so on and so forth. But we're going to use this to estimate the population proportion of diabetes. Okay, so I'm going to call the population proportion, I'm going to call it P. Okay, P is never going to be known to us because in order to know what P is, the population proportion, we would have to know, we would have to sample every person in the population. Okay, so now instead, I'm going to say to myself, well, this sample of 1,000 people is pretty good representation of what the population is concerned if it's really random, right? So I'm going to guess that P is somewhere around 20% or 0.20. Seems like a reasonable assumption, doesn't it, right? So the only problem is that I want to distinguish between the population proportion and the sample proportion. Sample proportion, I'm going to put a little caret. A little symbol's called a caret, a cap on it. So P cap, as we sometimes say, if I can't spell it out occasionally, you'll see me write out P cap. If I'm on a typewriter or a keyboard and I can't easily get to that symbol and put it on top of the P. So P cap is equal to 0.2. In other words, 20% of the sample that I've taken has diabetes. Well, what is a sample of 1,000? If I did that over and over again, what would it look like? Well, first, I'm going to take a small sample. I'm going to say a sample of, say, 100, much smaller sample, right? Let's say that P cap came out to be, say, 23%, 23 out of 100 people had diabetes. Well, if I took a sample of size 100 over and over and over again, right? Let's assume for a moment that we had a good guess there and the population proportion was really 2.0, but we really don't know for sure what it is. What would a sample of 100 people look like if I did it over and over and over again? So one time I might get P cap is equal to 0.23. The next time I sample another 100 people in the same population, maybe I'll get 0.18. Next time I do it again, maybe I'll get 0.25. Next time, maybe I'll get 0.20. Maybe I'll get lucky and hit it right on the head. Next time, maybe I'll be much lower. It's equal to 0.15, right? So if I take those, if I repeatedly sample samples of size 100 and I gather up all the proportions that I got, well, I know that most of these proportions are going to be pretty close to the population proportion. And the distribution, as it gets further away, right, I'm going to get fewer and fewer instances where my proportion is much smaller or much bigger than the true population proportion. In other words, I'm going to get a normal distribution. And this normal distribution of many, many, many samples of size 100 is going to be centered. The mean of these, half time it's going to be higher than what the population really is. Half time it's going to be lower just by chance. The mean is going to be the same as the population proportion. And then it'll be distributed in such a way that all of my samples will be normally distributed. And we know when we have a normal distribution, for instance, I know that I can say that 95% of these sample results are going to be between 2 standard deviations below the mean and 2 standard deviations above the mean. In reality, we really know that's 1.96 below the mean and 1.96 above the mean if we want to be a little bit more accurate. So 95% of them are going to be between there and there. So whenever I take a sample, I know that the sample size is going to determine what this spread is. So when I take my sample, repeated samples of size 1000, again, the mean of all the samples of size 1000 is going to be 0.20, just like the mean if I took enough of them. But my width, the width of my distribution is going to be much narrower because it's 1000, they're all going to be conceivably closer to the real population mean than maybe some of the scattered results I might get if the sample size were only 100. So in this case, this distance of 2 standard deviations above to 2 standard deviations below is narrower than this distance. It's the 2 standard deviations. It's a narrower range if a sample size is larger. So in other words, I need to know what the standard deviation for my repeated samples is for that sample size before I can get an idea of where 95% of the samples would wind up, right? So I need to know that standard deviation of my samples. Well, the standard deviation of our samples, we commonly call that the standard error instead. And that standard error can be calculated if we're dealing with a population mean, a numerical mean. We say that that's equal to the standard deviation of the population, which we call sigma, over the square root of the sample size. So you can see as n gets bigger, sample size gets bigger, the standard error, the width of this distribution, normal distribution of our sample means, gets narrower. When we have a proportion, that's going to be a little bit different. The formula that we use to determine the standard error for a proportion is equal to the square root of the proportion, whatever it happens to be, population proportion, times 1 minus the proportion over the sample size. Well, just like in situations where we don't know the population standard deviation, just like we don't know the mean, right? Well, then we often put in the standard deviation of the sample. Best that we know it, that's our best estimate of standard deviation of the population is what we get from our sample itself, the sample standard deviation. Similarly, the P that we use here, since we're never going to know what P really is for the population, we use what P cap is instead. So let's go back to our issue here with our diabetics. So my sample size 1,000, 200 people turn out to be diabetic. My sample proportion is 0.20. So now my standard error would be equal to the square root of 0.2, 0.8, 1 minus P, over the sample size, which is 1,000. Okay, so I'm going to put up my calculator and I'm going to calculate that. Whoops. Okay, so it's going to be 0.2 times 0.8 is equal to 0.16 divided by 1,000 is equal to 0.00016. I'm going to take the square root of that. I'm going to take the square root of that whole thing. And it comes out to be 0.012649. For our purposes, I'm going to round that to 0.013 for our purposes. Maybe you should take an extra decimal place when you're working. You always run around at the very end, but for convenience right now, while working, I'm going to call that 0.013. So our standard error is equal to 0.013. Now, you may remember that we had a formula for the calculation of a 95% confidence interval. In other words, even though we may never know what the true population proportion is, now that we've done this sample of 1,000 people, we can at least, having our understanding or how sample size affects the how close or how variable the sample results are going to be. Since we know that now, we can create a confidence interval within where we have a certain level of certainty as to what the true population proportion is. And that formula is going to be, and remember, the way we used that formula before when we were working with means, with numerical variables or means, we said that that confidence interval was equal to X bar plus or minus some Z value or T value if it's a very small sample times the standard error. Okay, so I'm going to calculate what Z is going to be. What is Z going to be? Well, my confidence interval is going to be 95%. And we know if we have a large sample size, our value of Z for a 95% confidence interval, in other words, alpha over 2 is equal to 0.025. In other words, alpha is equal to 5%, same thing. In other words, 5% tolerance from being wrong, okay, is equal to 1.96. Okay, and you remember that if we wanted a 99% confidence interval, it's going to be 2.58, and a 90% confidence is going to be 1.64. So lower confidence is going to be a narrower range, higher confidence, we make the range wider to be more certain that we actually capture the population mean. So that's the formula for a mean. Formula for a proportion is going to be P cap plus or minus the Z value. And again, this could also be a t-score instead with a numerical variable times our standard error. Okay, so in the case of a proportion, most of the time we're dealing with a very large sample size. Even 100 is a pretty big sample size. But very often we're doing population surveys where, where our sample size might be 1,000, 5,000, so on and so forth. So for the most part, when you're doing a proportion, a confidence interval proportion, this is usually almost always going to be 1.96 P cap plus or minus 1.96 times our standard error. We just calculate our standard error to be 0.013. So I'm going to go ahead and multiply that out and find out what I get. Again, bring up my calculator. So let's clear everything first. So 1.96, 1.996 times 0.013 is equal to 0.02548. Now notice I already kind of built in a bit of an error here because I didn't really use all the digits that I had before. You really should consider using some extra digits. I'm speeding things up here a little bit by doing this. Very often I'll work with Excel, which no matter what you're displaying, it maintains all of the digits in your calculation anyway. So this is our standard error, our Z-score times for our level of confidence and our standard deviation or our standard error for our sample proportions, right? So that's 0.0258. I'm going to put that into memory. Let me put it out first. I'm going to put that into, so it's going to be P cap plus or minus 0.025. Again, I rounded it. You shouldn't round quite as much as I did. I'm expediting this a little bit, 0.025. Now this quantity that we're going to add and subtract from P, okay, which is really Z times the standard error, right? That quantity we're adding and subtracting, we give that a special name. We call that the margin of error. So we're going to add and subtract the margin of error. That's just a new name for this value multiplied out. So we're going to take our p-value, which is 0.20 from our sample, plus or minus 0.025. So we're going to subtract it, and then we're going to add it to get two numbers. So I'm going to bring back my calculator. Okay, first thing I'm going to do, make sure my memory is cleared out. And then I'm going to add this quantity to memory. And then I'm going to clear that calculation. So I'm going to take my 0.20. I'm going to subtract, and I'm going to recall memory in order to do that, our 0.025. And it comes out to be 0.17. I'm going to call that 0.175. And I'll write this down. 0.175. I'll put a comma here, and parentheses up front here, and then I'm going to go back here again. This time I'm going to add my margin of error. So I'm going to clear this. I'm going to say 0.20, our sample proportion, plus our margin of error is equal to 0.225. 0.225. So we are 95% confident that the true population mean, which we don't know, we don't really know it, all we know is our sample proportion came out to be 20%. Our population proportion, we'll never know it, but we're 95% certain that it's between 0.175 and 0.225. Had I wanted to know it with 99% certainty, I would have used, instead of 1.96, I would have used 2.58. And if I used 2.58 in there, what would have happened? 2.58 times 0.013 is going to be a bigger number. So our margin of error is bigger. So we're going to have a smaller number here, a bigger number here. It's going to be a wider range, hence the higher level of confidence. And if we wanted a 90% confidence interval, we would have used 1.64, just like we would have if we were dealing with a mean of a sample instead of a proportion. Okay, so that's the way we would figure it out for other confidence intervals. That's 95% confidence that it's between these two numbers. Now, there's a 1 in 20 chance, of course, that the true population proportion might be higher or lower than this range. It might be 0.16 or 0.23 or something like that, right? But we're willing to accept that chance because in order to make this a practical calculation, right? Because if we wanted to know absolutely for sure, the only way to know that would be to sample the entire population. And we don't generally usually have the resources to do that, except perhaps the government when they do a census every 10 years, where they actually count every person in the population. So I'm going to review an example in assignment 3A that uses this procedure. So let's give that a try. So let's take a look at what we have in assignment 3A. Okay, so let's see what we're asked here. I'm gonna have to I'll read this to you because I imagine it's pretty small on your screen, and I don't think blowing it up in this form is going to really help with them. Maybe a little bit. Okay. The probability that an infant is born prematurely in Mexico is 0.15. What is the standard deviation? So in other words, we're told what the population proportion is. The probability an infant is born prematurely in Mexico is 0.15. No sample involved there, right? Not yet, at least anyway. What is the standard deviation or standard error for the proportion of premature births for repeated samples from this population from size n equals 625? In other words, if we took a sample of 625 births in Mexico, and knowing that the population proportion is 0.15, what would we expect the standard deviation of samples that we took over and over and over again of this sample size to be? Okay, so let's take a look at what that might look like. So 0.15 in a sample size of 625. So the true population proportion is equal to 0.15. And we're going to take a sample from there of 625. So what would our standard error, if we took repeated samples, like our first sample, p-cap in our first sample might come out to be 0.14. p-cap in our second sample might come out to be 0.16. p-cap in our third sample might become 0.15. You know, our next sample might be 0.19, so on and so forth. What would our distribution look like if we took repeated samples of size 625 from this population? In this case, we know what the proportion is. What would this distribution of samples look like? It would have a mean of 0.15, just like the proportion for the population, because we're taking many, 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 many times. But how spread out would be? What would the standard deviation be of this population. Well, standard deviation is what we, of this repeated samples, right? Standard deviation, we call that the standard error. And again, we said that the standard error is the square root of P times 1 minus P over the size of the sample. The bigger the sample size is, the smaller the standard error is, meaning that this is a narrower distribution. Okay, so what is the standard error in this case? Well, the standard error is going to be equal to the square root of 0.15 times 0.85 over 625. Okay, so I'm going to give that a whirl here. Okay, I'm going to clear this. And I'm going to say 0.15 times 0.85. Whoops. Try that again. Let me clear everything out here first. 0.15 times 0.85 is equal to, divided by 625. Whoops. I'm going to have to start again, unfortunately. 0.15 times 0.85 divided by is equal to, divided by 625 is equal to, and the square root of that is going to be 0.014. Again, I'm rounding. I don't want you to round that dramatically when you do it, but until the very end. And I'm going to, but to expedite things, I'm going to call that 0.014. So our standard error is equal to 0.014. Okay, that's all we're asking for there. In that particular problem, that's all we're asking for. Okay, let's take a look at the next problem. The probability that an infant is born in Mexico prematurely is 0.15. What is the margin of error for the proportion of premature births for repeated samples of 625? You got a little hint there that that's equal to the z-score times the standard error. You probably remember that from when we just reviewed that a second ago. So what is our margin of error? Our margin of error is equal to whatever the z or t score is. If it's a really small sample, we would use a t-value, the t-table. But let's not worry about that now, because with proportions, we're almost always dealing with very large samples. So the z-score for a 95% confidence interval, I don't know if it stated it there, but it should have stated there that's for a 95% confidence interval. But I think most of you probably would have assumed that anyway, since that's the most common one that we calculate. A z-score times our standard error is our margin of error. Remember that formula of confidence interval was P cap plus or minus the z value for alpha is equal to whatever 5%, or alpha over 2 is equal to 0.25% for just one, to illustrate just one, that each tail has 2.5%, but it's real, still it adds up to 5% chance of being wrong, times our standard error. Well, this part is our margin of error. So what is it in this case? It's equal to 1.96 for a 95% confidence interval. Again, not stated, but assumed in the problem. Okay, times our standard error, which is 0.014. Let's see what we wind up with there. Okay, times, times 1.96, standard error was already there, is equal to 0.02799. So I'm gonna clear memory. I'm gonna put this into my memory. Then I'm gonna clear our margin of error is 0.027, say 0.028 if you want to round it off a bit. Okay, but I'm gonna hold that because there's no reason for me, since I can just throw it into memory, no reason for me to truncate that or to round that at this stage. So that's in memory right now. That's our margin of error. So I'm going to clear the register up here, right? Still in memory though, and I'm going to go to the next question in our problems. And what was the next question? The next question is, we would expect 95% of the proportions for samples of size 625 to be between this and the next problem is this. So we would expect 95% of our sample proportions to be between these two values. Really, we're asking for the same thing as the confidence interval for P, given that you know what the population is. This is really kind of working around the fact that we already know what the population proportion really is. So this would be the same thing as calculating our confidence interval. So how would we calculate our confidence interval in this problem? Well, it would be equal to what we think what our sample had given us. In this case, we actually know what the population proportion is. It would be equal to P plus or minus our margin of error, our Z times our standard error, right? Which is P plus or minus our margin of error, right? Which is 0.15 plus or minus our margin of error, which was, if I still have it there handy, nope. Back. Oops, I lost it. I guess somebody, let's see if we can record it. 0.0028 plus or minus 0.0028. So what would that be? That would be at the lower end. That would be, and let me go in here and calculate that. So I'm going to clear that. I'm going to say 0.15 minus our margin of error. And that would be 0.122. I'm going to try and remember that. Clear. And I'm going to add 0.15. I'm going to take 0.15 and add our margin of error. Okay. 0.179. No, I already forgot the first number. 0.1, I'm going to call that 178. 0.178. Okay, it's added, it's been added. And I think this was 0.122. If I'm wrong, you guys can correct me. Let's see. 28 added to that would be 0. Yeah, it's going to be 0.122. I actually did manage to remember it. So that's our 95% confidence interval, the lower range and the upper range. In this case, it's a little bit of, it's really telling us what the range of 95% of our sample size 625 would be if we took it over and over and over again. And this were really true about the population. But in any case, we're calculating, it's the same way that we calculate the confidence interval. Okay, so I hope that clarifies this issue of calculating a confidence interval for a proportion, or a dichotomous variable. How many people, what percentage of people in the population are right-handed? What percentage are diabetic? What's the probability that so-and-so would get 30% of the vote or something like that? Okay, so if you have questions, post them into the discussions forum on Blackboard, and I will post this video. So it's available to you to review when you decide you need some help on the homework or you need to review this concept.